Welcome, everyone, to Lecture 12 of GFE0007, Data Analytics Made Easy for Beginners. Today, we are going to cover what I consider one of the most exciting and varied lectures of the entire course. We are calling it Other Data Science Tasks and Techniques, but do not let that humble title fool you. What we are going to study today are some of the most widely used and genuinely powerful techniques in the modern data science toolkit. Over the past 11 weeks, we have built up a solid foundation. We have covered probability, classification, regression, clustering, text mining, and analytical engineering. Today, we are going to branch out from those core supervised learning techniques and explore a much richer landscape. We are going to ask, what happens when the problem is not a simple classification or regression? What do you do when you want to discover patterns among items that go together? When you want to understand what is normal and detect what is unusual? When you want to predict connections between people? When your data is too large to work with directly? When one model is not good enough on its own? And when you want to understand not just correlation, but actual cause and effect? These are the questions that define the frontier of practical data science, and today we are going to equip you with frameworks and intuitions to tackle each one of them. So let us get started. Section 1, the analytical engineering mindset. Let me begin by grounding us in something very important before we dive into the technical content. When you study data science in a university course, datasets are handed to you pre-cleaned and neatly packaged. A textbook might say, here is a dataset of customer purchases. Apply a naive Bayes classifier to predict whether a customer will buy again. The problem type is labeled for you. The data is ready. The evaluation metric is suggested. You follow the recipe. Real business life is nothing like that. When you sit down with a product manager, a marketing executive, or a chief operating officer, they are not going to hand you a classification problem. They are going to describe a business challenge in business language. They might say, our customers are leaving us and we do not know why. Or, we have all of this transaction data but we do not know what to do with it. Or, we think there are patterns in how our users behave, but we cannot identify them. That gap between a messy business problem and a clean data science solution is where the concept of analytical engineering comes in. Analytical engineering is the process of designing an analytical solution based on the data, tools, and constraints available. It is a deliberate integration of human knowledge and computer-based techniques. It is engineering because it involves design choices, trade-offs, and constraints. It is analytical because it is grounded in data and mathematics. And together, these words describe exactly what a skilled data scientist does every day on the job. Keep this framing in mind throughout today's lecture. Every technique we cover today is a tool, and part of your job as an analytical engineer is to recognize when each tool is appropriate. At the heart of analytical engineering are two complementary mental processes: decomposition and recomposition. Let me explain each one carefully. Decomposition means breaking a messy, complex, and often ambiguous business goal into smaller, more manageable subtasks. Subtasks that individually match patterns we already know how to solve in data science. A big problem that feels overwhelming and impossible becomes tractable when we decompose it into pieces. For example, if someone asks you to reduce customer churn, that is not a data science task in itself. But you can decompose it into a task of predicting who is at risk of leaving, a task of identifying which customers are persuadable, a task of estimating the value of each customer, and so on. Now each of those pieces is something you can model. Recomposition, on the other hand, means taking the outputs of all those individual subtasks and combining them back together into a final decision-making framework. The individual models and analyses do not stand alone. They need to be brought together coherently so that the business can act on them. Here's an important insight from this slide. A churn problem is not just about predicting who leaves. That is actually a naive formulation of the problem. A more sophisticated formulation asks, who among the people likely to leave can be influenced to stay? That is a fundamentally different question, and it requires a different decomposition. You need to estimate both the probability of leaving and the probability of responding to a retention offer. These are two separate models that you then recompose into a single targeting decision. This is analytical engineering in action. Let me now walk you through the roadmap for today's lecture. We have 6 major topic areas that we will cover in sequence. Each one is a distinct data science capability that extends beyond the classification and regression techniques at the core of most introductory courses. First, we will look at co-occurrences and associations, the foundation of market basket analysis, which answers the question, what items tend to go together? Second, we will cover profiling and anomaly detection, the art of characterizing what is normal, which gives us the power to spot what is abnormal. Third, we will study link prediction, which is the task of predicting whether a connection should exist between two entities in a network. Fourth, we will explore data reduction and latent information, techniques for dealing with large, high-dimensional data by uncovering hidden structure. Fifth, we will examine ensemble methods, the insight that many models working together can outperform any single model. And sixth, we will close with causal reasoning, perhaps the deepest and most philosophically rich topic of the entire course. These 6 areas form a rich and diverse toolkit. Some of them are unsupervised. There is no target variable. Some of them blend supervised and unsupervised thinking. All of them represent genuine, practical tools used in industry today. Let us begin. Section 2. Co-occurrences and association discovery. Our first major topic is association discovery, which is also commonly called market basket analysis. The core question it answers is beautifully simple. Which items tend to occur together? The classic setting is a grocery store or a retail outlet. Imagine you have a database of millions of customer transactions. Each transaction is a basket, a set of items that one customer purchased together in a single shopping trip. Association discovery asks, are there pairs or triples or larger groups of items that appear together in baskets more often than you would expect by random chance? But, and this is important, the concept of a basket and items is far more general than groceries. The items could be movies that a user has rated. They could be articles a reader has clicked on. They could be symptoms a patient has reported. They could be pages a website visitor has viewed. They could be skills that job candidates list on their profiles. Anywhere you have transactions and collections, you have the potential for association discovery. The business value of this technique is enormous. If you know that customers who buy item A also frequently buy item B, you can place these items near each other in the store, recommend B when someone adds A to their cart, or design promotions that bundle A and B together. Online retailers like Amazon have built significant revenue on exactly this kind of analysis. Customers who bought this also bought that. Now the key challenge is defining interesting. Not all co-occurrences are interesting. Bread and milk co-occur often, but that is because they are both extremely popular items. The fact that they appear together tells you almost nothing actionable, so we need formal measures of interestingness. The next 3 slides introduce the 3 most important ones: support, strength, and lift. The first measure is called support. Support measures the prevalence of an association in the total dataset. Formally, the support of items A and B together is simply the probability that both A and B appear in the same transaction, which we write as P of A, dash B. So if out of 1 million transactions, 50,000 contain both item A and item B, then the support of this association is 50,000 divided by 1 million, which is 5%. Why do we care about support? Because support acts as a complexity control. Imagine you are looking for interesting associations, and you find that 2 very obscure items co-occur in exactly 1 transaction. That is a 1 in a million event. Is it interesting? Almost certainly not. It could be a data entry error. It could be a coincidence. It is statistically meaningless because the sample size supporting the association is too small. Support tells us, this association is not just a statistical fluke on a tiny subset of data. It actually occurs with some regularity across the dataset. In practice, analysts typically set a minimum support threshold. For example, only consider associations that appear in at least 1% of all transactions. This filtering dramatically reduces the search space and ensures we are only looking at patterns that are genuinely prevalent. Think of support as the first filter. It tells you the association is common enough to be worth investigating, but support alone is not enough. An association can be highly prevalent and still be completely uninteresting. That is where our next measures come in. The second measure is called strength, which is also widely known as confidence. Strength measures the directional conditional probability of an association. Specifically, the strength of the rule A implies B is the probability that B occurs given that A has already occurred. In formal notation, we write this as P of B given A. Let me unpack why the word directional matters here. Unlike support, which is symmetric, the support of A and B is the same as the support of B and A. Strength is asymmetric. The strength of the rule A implies B is not the same as the strength of the rule B implies A. These two rules mean different things and should be evaluated separately. Let us make this concrete with the example on the slide. Suppose someone has purchased an e-watch. What is the probability that they also purchase the e-bracelet? If the answer is 5%, we say the strength of the rule e-watch implies e-bracelet is 5%. This has a clear and direct business interpretation. Out of every 100 e-watch customers, approximately 5 also purchase the e-bracelet. That is actionable. It tells you that a cross-sell opportunity exists. However, strength alone can also be misleading. Imagine that the e-bracelet is purchased by 80% of all customers, regardless of what else they buy. In that case, a 5% strength for e-watch implies e-bracelet actually tells us that e-watch buyers are less likely to buy the e-bracelet than the average customer. A high strength value is only impressive when it is high relative to the base rate. This is exactly the problem that our third measure, lift, is designed to solve. Lift is the measure that makes association analysis genuinely powerful and genuinely interesting. Let me explain it carefully, because it is a beautiful idea. Lift measures how much more likely the co-occurrence of A and B is compared to what we would expect purely by random chance. The formula for lift is lift of A comma B equals P of A comma B, the joint probability divided by P of A times P of B, the product of the individual probabilities. Let me explain the denominator. If A and B were completely independent of each other, if buying A had absolutely no relationship with buying B, then by the laws of probability, the probability of both occurring together would simply be P of A multiplied by P of B. This is what we call the expected probability under independence. So the denominator in the lift formula represents the baseline. This is how often A and B would appear together if they had zero relationship. The numerator is the actual observed probability. So lift is asking, how does reality compare to the independence baseline? If lift equals 1, the items appear together exactly as often as random chance would predict. There is no real association. If lift is greater than 1, the items appear together more often than chance. There is a genuine positive association. If lift is less than 1, the items actually appear together less often than chance would predict. They are negatively associated, meaning buying A makes it less likely that B will also appear. This is the magic of lift. It filters out the obvious. Bread and milk co-occur frequently, but their lift might be close to 1 because both are individually popular. Lift forces us to look beyond raw frequency and find genuinely surprising, non-obvious patterns. High lift associations are the truly interesting ones, the ones that can drive actionable and profitable business decisions. Example, beer and lottery tickets. Let us now work through a concrete numerical example to make the lift calculation completely clear. This is a famous and intuitive example involving beer and lottery tickets. Suppose we have a large data set of retail transactions. We observe that 30% of all transactions include beer. So we write P of beer equals 0.3. We also observe that 40% of all transactions include lottery tickets. So P of lottery tickets equals 0.4. Now, if beer and lottery tickets were completely independent, if buying one had nothing to do with buying the other, what fraction of transactions would contain both? Under independence, we simply multiply the two probabilities. 0.3 times 0.4 equals 0.12. So we would expect both items in 12% of transactions. But when we actually look at the data, we find that 20% of transactions contain both beer and lottery tickets. The actual observed probability is 0.20. This is noticeably higher than our expected 0.12. Now we compute the lift. Lift equals 0.20 divided by 0.12, which is approximately 1.67. What does this mean in plain English? It means that buying both beer and lottery tickets together is 1.67 times more likely than pure random chance would predict. There is a genuine positive association between these two items. This is a real and well-known finding from retail analytics. These two items, beer and lottery tickets, are surprisingly co-purchased. A retailer who discovers this might place lottery ticket machines near the beer aisle, or create a joint promotional display. The lift value quantifies the surprise in the pattern and gives a clear signal about where to act. Now I want to show you how radically this framework generalizes beyond retail. This is one of the most intellectually exciting aspects of market basket analysis. The concept of a basket can be redefined for almost any domain. Consider social media. On Facebook, a user can like pages, artists, shows, movies, books, and ideas. If you think of each user as a transaction and their full set of likes as their basket, then you can apply association discovery to understand which likes tend to cluster together. High-lift associations tell you about cultural tastes and the surprising connections between them. The slide gives us some fascinating real-world high-lift examples. Consider the association. Liking Family Guy and liking The Daily Show strongly predicts liking The Colbert Report. This makes cultural sense. These shows share a similar audience, demographic, and humor style. But the power of association analysis is that you can discover this computationally from data, even without knowing in advance that such a cultural cluster exists. Another example from the slide, liking the animated film Spirited Away strongly predicts liking Howl's Moving Castle. Both are Hayao Miyazaki masterpieces. The data discovers this fan community automatically. Now here is a particularly powerful and somewhat provocative extension mentioned on the slide. You can include non-like data in the basket. For example, you might include an indicator like high IQ derived from survey data, and then look for what Facebook likes correlate with it. This kind of analysis has been used in academic research to discover surprising associations between digital behavior and demographic traits. It raises important ethical questions that we should always keep in mind. Just because we can compute an association does not mean it is appropriate to act on it. But as a demonstration of the technique's power, it is remarkable. Section 3, Profiling and Anomaly Detection. Our second major topic is profiling. Profiling means characterizing the typical behavior of an individual, a group, or a population. The goal is to build a model of what is normal. What does typical behavior look like? So that you can then detect deviations from that normal. The most widely cited application of profiling is fraud detection. Think about your credit card. Every time you use your card, your bank is running a real-time profiling model in the background. This model has learned what your normal spending behavior looks like, where you typically shop, how much you typically spend, at what times of day and week, in which geographical regions. Your profile captures the statistical fingerprint of your typical financial behavior. When a transaction occurs that is sharply inconsistent with your profile, say a large purchase in a foreign country at 3 a.m. when you have never made an international purchase before, the system flags it as a potential anomaly. It is not definitively labeled as fraud. It is labeled as an outlier relative to your profile. A human review or additional authentication step may then follow. This is a profound use of data science. You are not building a supervised model with labeled fraud examples, although that is also useful. You are building an unsupervised characterization of normality and then detecting deviations. Profiling is closely connected to model fitting. You are finding the parameters of a statistical model that best represent the typical behavior of the data. Once you have fit that model, any data point that the model considers extremely unlikely is flagged as anomalous. Now, how do we actually build a profile? The most naive approach is to just compute the mean, the average, of each variable. But this slide highlights a crucial cautionary lesson that every data scientist must internalize. Simple averages can be deeply misleading. Let us consider a concrete example involving call center wait times. Suppose you compute the average wait time across all callers and get a number like 4 minutes. You might think, okay, the typical customer waits 4 minutes. Our service level target is 5 minutes, and we are meeting it. But what does the distribution actually look like? If the distribution of wait times is skewed, if it has a long right tail, meaning there are a small number of callers who wait very, very long times, then the mean is being pulled upward by those extreme values. The mean may be 4 minutes, but the median, the wait time of the actual middle caller, might be 2 minutes, and there may be a tail of callers waiting 15 or even 20 minutes. The mean of 4 minutes does not accurately represent any typical caller's experience. It is an artifact of the arithmetic. This is what we mean when we say that skewed data pulls the mean away from what is truly typical. In this kind of situation, the median, the value at the 50th percentile, is a much more robust and honest characterization of the center of the distribution. The broader lesson here is one of the most important habits of data analytic thinking. Always visualize the distribution before you trust a summary statistic. If the distribution is not approximately a symmetric bell curve, what we call a normal distribution or Gaussian distribution, then the mean alone is not sufficient. You should consider the median, the quartiles, the full shape of the distribution, and potentially data transformations like taking the logarithm to make a skewed distribution more symmetric. Now let us move to a more advanced and powerful profiling technique, Gaussian mixture models, or GMMs. This technique addresses a limitation that both simple averaging and even standard profiling have, namely, what if the population is not homogeneous? What if it is actually composed of several distinct subpopulations, each with its own typical behavior? Let me give you a concrete example. Imagine you are profiling the spending behavior of credit card customers. There might genuinely be two types of customers in your portfolio: budget-conscious shoppers who make frequent small purchases, and high-value shoppers who make occasional large purchases. If you try to fit a single profile to both groups together, you will get a muddled average that accurately describes neither group. You will be confused by the mix. A Gaussian mixture model solves this by assuming that the population is made up of k distinct subgroups, where you choose k, and each subgroup has its own bell curve distribution with its own mean and its own spread. The model learns these k distributions from the data automatically, without you telling it which data point belongs to which group. The output is a soft clustering, which is a key concept. In hard clustering, like simple k-means, each data point is definitively assigned to exactly one cluster. In soft clustering, each data point belongs to each cluster with a certain probability. A customer might be 70% likely to belong to the, quote, budget shopper group, and 30% likely to belong to the high-value shopper group. This probabilistic membership is more realistic and more mathematically honest than forcing a binary assignment. For profiling and anomaly detection, GMMs are particularly powerful because they can capture the complexity of a multimodal population and flag anomalies precisely. A data point that has low probability under all k-component distributions is a genuine outlier relative to the entire population model. Section 4, Link Prediction and Social Recommendation. We now turn to a fascinating and increasingly important family of tasks known as link prediction. The fundamental question here is, given a network of entities and the connections between them, can we predict whether a new connection, a new link, should exist? The examples on the slide are ones you encounter every day in your digital life. When LinkedIn shows you people you may know, it is running a link prediction model. When Netflix suggests a movie you have not seen, it is predicting that a link between you and that movie should exist, that you would rate it highly. When Spotify curates a playlist, it is predicting links between you and songs. There are two main ways to think about link prediction. The first is as a similarity problem. The intuition is that similar entities should be linked. If you and another LinkedIn user have attended the same university, worked in the same industry, share many mutual connections, and have similar job titles, then by similarity you are likely to know each other or benefit from connecting. The link prediction algorithm computes a similarity score between pairs of entities and recommends the highest scoring pairs. The second framing is as a predictive modeling problem. Rather than just computing similarity, you engineer features from the network structure and the entity attributes, and then train a classifier to predict whether a link exists. This is more flexible and powerful because it can incorporate any kind of information you have about the entities and their existing connections. Link prediction is a beautiful example of how data science problems can be reformulated. A social recommendation problem becomes a classification problem. A movie recommendation problem becomes a regression problem. The key is the analytical engineering skill of recognizing the underlying structure. When we decide to treat link prediction as a standard supervised learning problem, we immediately face an interesting question. What is an instance? In a standard classification problem, an instance is a single entity, a customer, a patient, an email. But here, we are not predicting a property of a single entity. We are predicting the existence of a relationship between two entities. So what should an instance look like? The answer, as the slide tells us, is that an instance is a pair of individuals. Each row in our training dataset represents a pair of entities, say person A and person B, and the label for that row is, does a link currently exist between them? If yes, the label is 1. If no, the label is 0. Now we need features to describe each pair. And this is where the analytical engineering creativity comes in. We ask, what characteristics of the pair are predictive of whether a link should exist? The slide gives us several natural candidates. the number of common friends or connections. If A and B already share many mutual connections, a direct connection between them becomes more likely. The similarity of their interests or attributes. If A and B both have a strong interest in machine learning and both live in the same city, they are more likely to connect. Geographical proximity. Physical nearness often predicts social connection. We can also include structural network features. For instance, whether A and B belong to the same community within the network, or how short the shortest path between them already is through their mutual connections. All of these become features in a standard feature vector, and then a standard classifier. Logistic regression, a decision tree, a random forest, can be trained on historical data where link formation is known. This is a perfect example of the analytical engineering mindset in action. A problem that initially looks unique and specialized, predicting social connections, turns out to reduce to a standard supervised learning problem once you engineer the right representation. Data reduction and latent information. We now turn to the topic of data reduction and latent information. This section addresses a challenge that is ubiquitous in modern data science. What do you do when your dataset is simply too large, too high-dimensional, or too noisy to work with directly? Consider a user item ratings matrix in a recommendation system like Netflix or Amazon. You might have tens of millions of users and hundreds of thousands of movies or products. The matrix that represents all possible user item interactions has tens of trillions of potential entries. Even with modern computing power, working directly with a matrix of this size is computationally prohibitive. Furthermore, the matrix is extremely sparse. Most users have rated only a tiny fraction of all available items. Most of the entries are missing. Data reduction is the process of replacing this large, unwieldy, sparse dataset with a smaller representation that preserves the important information while discarding the noise and redundancy. There is always a trade-off involved. You lose some fine-grained detail in exchange for computational manageability and conceptual clarity. But here is the key insight that makes data reduction so powerful. Often, the reduced representation is actually more informative than the original data. Why? Because the original data is noisy and high-dimensional. A reduced representation can capture the underlying structure, the signal, while averaging out the noise. A model trained on a thoughtful, low-dimensional representation often generalizes better to new data than a model trained on the raw, high-dimensional input. Less can truly be more. The most powerful concept in data reduction is the idea of latent dimensions. The word latent means relevant, but not observed explicitly. Latent factors are the hidden, underlying structure that explains the patterns we see in the data. The Netflix Prize example on this slide is the perfect illustration. When Netflix has a database of user ratings, each user gives each movie a score from 1 to 5 stars. What the data explicitly shows us is just numbers. A 3 here, a 4 there, a 1 somewhere else. We do not directly see any attribute that explains why user A gives certain movies high ratings, and user B gives a different set of movies high ratings. But intuitively, we know that movie preferences have underlying structure. There are movies that are cerebral and thought-provoking versus movies that are action-packed and viscerally exciting. There are movies that appeal emotionally versus movies that appeal intellectually. These are dimensions of taste that exist in reality, but are not recorded as explicit variables in the data. They are latent. Matrix factorization techniques, particularly singular value decomposition and non-negative matrix factorization, allow us to mathematically uncover these latent dimensions from the raw rating data alone. The algorithm looks at the patterns of who rates what highly and discovers that there are underlying factors that explain those patterns. It might discover that some users consistently prefer movies with high intellectual complexity, and some consistently prefer movies with high emotional resonance, even though nobody ever labeled movies with these attributes. The labels emerge from the mathematics. This is a profound capability. We are discovering structure that was invisible in the original data, structure that is real, meaningful, and actionable. Once we have extracted latent dimensions from our data, we can represent every entity, every movie, every user as a point in a multidimensional space. We call this a taste space, or a latent space. The slide describes a two-dimensional example to make this visual and intuitive. The first dimension runs from drama and heart at one end to action and gut at the other. Movies like a tender family drama sit at one end, action blockbusters sit at the other. The second dimension runs from intellectual to emotional. So a dry, cerebral documentary sits in one quadrant, action and intellectual. A tearjerker romance sits in another, drama and emotional. In this two-dimensional taste space, each movie is a point. Each user can also be represented as a point, based on the kinds of movies they have historically rated highly. Recommendation then becomes a geometric problem. Find the movies that are closest to a given user's position in taste space. If a user is located in the quote-quote-quote intellectual region, recommend the movies clustered in that region. This is what Netflix, Spotify, and Amazon are doing when they say, because you watched X, we recommend Y. The beauty of this approach is that it is entirely data-driven. Nobody sat down and said, let us define these two dimensions. The algorithm inferred them from millions of user ratings. The dimensions that emerge are the ones that actually explain the most variance in user preferences. They might not be labeled in human legible terms, but they are real and predictive. In practice, recommendation systems use many more than two dimensions, typically dozens or hundreds of latent factors, for maximum predictive power. But the geometric intuition remains the same at any dimensionality. Ensemble methods, a collection of experts. We now move to ensemble methods, which represent one of the most practically important ideas in all of machine learning. The fundamental insight of ensemble methods is, a collection of models working together will typically make better predictions than any single model working alone. An ensemble model is built by training many individual models and then combining their predictions, either by voting. In the case of classification, the class predicted by the majority of models wins, or by averaging. In the case of regression, the final prediction is the mean of all individual model predictions. Why does this work? The intuition comes from a wonderful idea in statistics and decision theory, sometimes called the wisdom of crowds. Imagine you ask many independent experts to estimate the weight of an object. Each expert makes an error, but the errors are random and in different directions. Some guess too high, some too low. When you average all of their guesses, the random errors tend to cancel out, and the average is often much closer to the truth than any individual estimate. The same principle applies to machine learning models. Each individual model makes some errors on the training data. But if the errors made by different models are at least partially uncorrelated, if different models are getting different examples wrong, then combining them causes those idiosyncratic errors to cancel out. The ensemble is more stable and more accurate than any individual component. This is not merely theoretical. Ensemble methods are among the most consistently winning approaches in real-world machine learning competitions and production deployments. Random forests, gradient boosting, and XGBoost, all of which you may have encountered already, are all ensemble methods. To understand why ensemble methods work as well as they do, we need to understand the sources of error in a machine learning model. This slide introduces one of the most important conceptual frameworks in all of machine learning theory, the bias-variance trade-off. Every prediction error can be decomposed into three components. The first is inherent randomness, sometimes called irreducible error. This is the noise in the data itself. No matter how perfect your model is, you cannot predict outcomes that are genuinely random. This is the floor on prediction error, and no algorithm can eliminate it. The second component is bias. Bias is the error that arises when your model is too simple to capture the true underlying relationship in the data. Imagine the true relationship between your input features and the target is a complex, non-linear curve. If you fit a straight line to this data, the straight line is systematically wrong everywhere. It consistently underestimates in some regions and overestimates in others. That systematic error is bias. A model with high bias is said to be underfitting. It cannot capture the complexity of the true pattern. The third component is variance. Variance is the error that arises when your model is too sensitive to the specific training data it was given. A highly complex model, say a very deep decision tree with no pruning, can memorize the training data perfectly. But it has learned the noise in the training data along with the signal. When presented with new, unseen data, its predictions are all over the place because they reflect training data-specific noise rather than general patterns. This is called overfitting. A model with high variance is overfitting. The fundamental challenge of machine learning is that bias and variance trade off against each other. Simple models have low variance but high bias. They are consistent but consistently wrong. Complex models have low bias but high variance. They can potentially fit anything but are unpredictable. Finding the sweet spot is the central challenge of model selection. Now we can explain precisely how and why ensemble methods work, using the bias-variance framework we just introduced. Consider a complex model, say a fully grown decision tree with no depth limit. Such a tree has low bias. Given enough data, it can approximate almost any complex pattern. but it also has very high variance. It is exquisitely sensitive to the specific training sample it saw. If you trained the same tree architecture on two different random samples of the same underlying data, you would get two quite different trees with quite different predictions. The variance is high. Now, suppose instead of training one such tree, you train 100 of them, each on a slightly different random subsample of the training data, or each considering a random subset of features at each split. Each individual tree is still high variance. But here's the key. The variance errors of the different trees are largely uncorrelated. Tree number 47 might overfit on one part of the feature space. Tree number 83 might overfit on a different part. When you average the predictions of all 100 trees, these uncorrelated errors cancel out. The ensemble has much lower variance than any individual tree. And crucially, the bias of the ensemble is approximately the same as the bias of each individual tree, low. So we end up with a model that has both low bias and low variance. We have escaped the trade-off, at least partially, by using the power of averaging. This is exactly why random forest, which averages many deep decision trees, is such a consistently excellent algorithm. This is why gradient boosting builds an ensemble sequentially, where each new model is trained to correct the errors of the ensemble so far. The principle is the same: strength through diversity and combination. Many imperfect models, combined wisely, create something much better than any single model: causal reasoning. We arrive now at our final and perhaps deepest topic: causal reasoning. This is a topic that sits at the boundary of statistics, philosophy, and data science, and it is one of the most commonly misunderstood and misapplied concepts in the entire field. Let us start with the most important mantra in all of statistics: correlation is not causation. Every data science student has heard this phrase, but what does it actually mean? And why does it matter so much in practice? Almost every predictive model we have studied in this course discovers correlations, patterns of things that occur together or variables that tend to move together. A logistic regression model for churn prediction finds variables that are correlated with customers leaving. A recommendation system finds items that are correlated with each other in user preferences. These correlations are real and often very useful for prediction, but they do not tell us why things happen. They do not identify cause. The slide gives us a perfect example of why this distinction matters so much in practice. It is sometimes called the viral marketing trap. Suppose you are analyzing social network data, and you observe that when one friend buys a product, their connected friends are more likely to also buy it. You might conclude, buying is contagious. If we can seed the network with early adopters, the purchase behavior will spread virally through social influence. But wait, there is an alternative explanation. Friends who are connected tend to be similar to each other in their demographics, interests, and tastes. If a product appeals to a certain demographic, it will appeal to their friends not because of influence, but because of shared characteristics. This is called homophily, the tendency of similar people to be connected. In this scenario, the apparent contagion is an illusion created by the underlying similarity structure of the network. Targeting friends of early buyers gives you no causal benefit because the buying happens due to shared taste, not social influence. This distinction, influence versus homophily, is not just academic. It has enormous practical implications for how you should design marketing campaigns and allocate budget. If influence is real, you invest in seeding strategies. If it is homophily, you invest in demographic targeting. Getting this wrong wastes significant resources. The counterfactual mindset. So how do we actually establish causation rather than mere correlation? The answer requires a fundamental shift in how we think about the question. We need to adopt what philosophers and statisticians call the counterfactual mindset. Causal reasoning asks a specific kind of question. What would have happened if things had been different? What would the outcome have been in a world where we had not shown the advertisement? What would the customer have done if we had not sent them a discount offer? What would the patient's health outcome have been if they had not received the treatment? These are counterfactual questions. The word counterfactual means contrary to fact. We are asking about an alternative reality that did not happen. And the challenge is that we can never directly observe both realities for the same individual. A customer either got the email or they did not. A patient either received a drug or they did not. We cannot go back in time and change one thing while holding everything else constant. The gold standard for answering causal questions is the randomized controlled experiment, what in business and technology is commonly called an A/B test. In a randomized experiment, you randomly assign subjects, customers, patients, users, to a treatment group and a control group. Because the assignment is random, the two groups are statistically equivalent on all other characteristics. Any difference in outcomes between the groups can therefore be attributed to the treatment itself, not to pre-existing differences between the groups. Randomization breaks the confounding. It eliminates the alternative explanations. When randomized experiments are not feasible, for ethical, logistical, or cost reasons, there are sophisticated observational analysis techniques such as propensity score matching, instrumental variable analysis, and difference in differences estimation. These attempt to approximate the conditions of a randomized experiment using observational data, though they are always subject to stronger assumptions and more scrutiny. The key practical distinction, and the one that should stick with you, there is a world of difference between identifying likely buyers, customers who are correlated with purchasing, and identifying customers who bought because of you. The first is achievable with standard predictive modeling. The second requires causal inference. Do not confuse them. Summary and final words. Let us pause and consolidate everything we have covered today. We have traveled a lot of ground, and I want to make sure the key ideas are clearly anchored in your mind. We started with association discovery, where the key concept is the lift measure. How much more likely is co-occurrence than random chance would predict? This technique is used for market basket analysis, recommendation systems, and discovering surprising patterns in any transactional data. We then moved to profiling and anomaly detection. The key concept here is norms and deviations from norms. We build a statistical model of typical behavior, potentially using Gaussian mixture models for heterogeneous populations, and flag deviations as anomalies. Applications range from fraud detection to quality control to cybersecurity. Next was link prediction, where we predict the existence or strength of relationships between entities. The key insight is that a pair of entities can be treated as an instance in a standard supervised learning problem, with network-derived features describing the pair. Then we covered data reduction and latent information. The key concept is that underlying high-dimensional data, there are often low-dimensional latent dimensions, hidden factors like quirkiness or intellectual appeal that can be extracted through matrix factorization and used for recommendation and analysis. Ensemble methods taught us that combining many models reduces variance without increasing bias, leading to consistently superior predictive performance. Building many diverse models and aggregating their outputs is one of the most reliable paths to high accuracy in practice. And finally, causality reminded us that correlations, no matter how strong, do not establish cause. Causal reasoning requires the counterfactual mindset, ideally realized through randomized controlled experiments, to determine what actually influences outcomes, rather than what merely co-occurs with them. Analytical engineering revisited. We started this lecture with the concept of analytical engineering, and I want to close by coming back to it, because after everything we have covered today, it should mean something richer and deeper to you than it did at the start. Data science is not a collection of isolated techniques to be applied mechanically. It is a combination of engineering and exploration. The engineering side means you are designing solutions under constraints, working with the data you have, not the data you wish you had, using the tools that are available, meeting the deadlines and resource limitations of the real world. The exploration side means you are genuinely curious, open to surprise, willing to follow the data to unexpected places, and committed to understanding not just what the model predicts, but why. The slide gives us a pointed piece of advice. Don't just apply a hammer to a nail. This is a gentle warning against the most common failure mode of newly trained data scientists, the tendency to take the one or two techniques you are most comfortable with and try to apply them to every problem. The world does not come to you labeled as classification or regression. As we saw today, problems might require association discovery, or profiling, or link prediction, or causal inference. You need to decompose each problem carefully, choose the right tool for each subtask, and always keep the ultimate business goal in mind throughout. Never lose sight of why you are doing the analysis. The best technical solution to the wrong problem is worthless. The most elegant model that nobody in the organization can understand or act on is worthless. Your job is to produce insight that drives good decisions and real business value. Final challenge. I want to close this lecture, and indeed this major portion of our course, with a quote attributed to Albert Einstein. If you can't explain it simply, you don't understand it well enough. This quote is not just a motivational poster slogan. For a data scientist, it is a genuine professional test. The techniques we have covered in this course, Probability, classification, regression, clustering, text mining, association discovery, ensemble methods, causal inference. All of them can be made mathematically complex enough to be incomprehensible. And there is a temptation, especially for technically talented people, to retreat into that complexity, to hide behind jargon and equations as a way of demonstrating expertise. But the true mark of expertise is the opposite: the ability to take something genuinely complex and explain it clearly to someone who does not have your technical background. When your CEO asks why the model recommended that marketing campaign, you need to be able to explain it. When a product manager asks why your recommendation system is suggesting certain items, you need to be able to explain it. When a regulator asks about the factors driving your credit scoring model, you need to be able to explain it. Your job as a data scientist is to bridge the gap between technical complexity and business value. Not just to run models, but to translate insights. Not just to optimize an objective function, but to connect that optimization to the decisions that matter. Not just to find patterns in data, but to tell a coherent story about what those patterns mean for the organization. That is what analytical engineering is, at its best. That is what this course has been trying to prepare you for. I am deeply proud of the progress you have all made over these 12 weeks, and I am confident that you are now far better equipped to face the messy, ambiguous, exciting challenges of real data science work. Thank you so much for your attention throughout this course. Good luck with your assessments, and I look forward to seeing the analytical engineers you will become. Take care, everyone.